So let's start. Thank you so much for joining us and donating your time and energy to us here.
Yes, I mean, it is really a great pleasure to talk about this work for Trinity, Japan. I mean, of course, I'm in Cambridge, so I visit Trinity regularly, not all the time, but regularly. I have been in Japan in the past fairly regularly, I mean, not for the past 6 or 7 years, but before that, a bit more often.
If you come, please let me know in advance, and I'll set up a dinner meeting with you here for our group.
And anyway, but the thing I would like to discuss is indeed, the title is Computer Simulations and Chemistry, but I should immediately say that most computer simulations in chemistry have to do with atoms, molecules, and reactions, whereas I'll be talking at a different level, namely at larger objects, colloidal particles, but also bioweapons like viruses. So you see here a few pictures. Can you see my pointer? I can also, wait a minute, I can do something about the pointer.
I can see your pointer, yes.
You see this pointer?
Yes, I can see.
Okay, good. So these are the things I'll be mainly talking about, and I hope that during my talk, the relation between these pictures will become clear, because the underlying topic of all the things I'll discuss is actually entropy as an ordering principle. And that sounds a bit counterintuitive, because that's not the way people usually speak about entropy, but I'll say much more about that in a minute. So this is a very brief introduction. And Gerrit, I mean, I assume it's okay if people interrupt me to ask questions. Is that right?
If you allow it, yes, of course.
I definitely
not so many
do
people, so it will be quite easy to contact.
Absolutely, you know, so that people shouldn't feel that they have to wait with their questions until the end, because it is quite possible that I write something that is unclear, and then if people don't ask immediately, then they may lose the rest of the talk. Okay, so I'll say something about entropy, and usually when I talk about this to students, I say, well, all students in the physical sciences are taught thermodynamics in the first or second year, and 95% of them hate it, and 5%, which includes people like me, they like it. But what I want to show is that really the core of thermodynamics is very simple and is based on observations. It's not some abstract mathematical framework to start with. And so to go back to the origin of thermodynamics, I'll show a picture of somebody that Gerrit and I just 10 minutes ago discussed, and that is this person, Sadi Carnot. And Sadi Carnot lived in France in the early 19th century. He died relatively young, and he was interested in the problem, what is the maximum amount of work that you could get out of a steam engine for a given amount of fuel. The interesting thing about Carnot is that he basically laid down the entire framework for what was to become thermodynamics, except that he did not create thermodynamics. So he was looking at heat and work, and at that time, the current theory was that heat itself was a conserved quantity. So it was more like heat was flowing through the machine, through the steam machine. Sorry. And the amount of heat going in was the same as the amount of heat going out, a bit like water in a turbine. And later on, people realized that actually it is not heat that is conserved, but energy, that is heat plus work. And that was the starting point of thermodynamics as we now know it. But Carnot already felt that there was something slightly wrong about the current view of heat. And so this is what can you see this? Let me just see, for me, it's...
yes, it's perfect, yes.
Okay, yeah. So, because Carnot said that if you have a machine that goes through a cycle, then he says it is found to contain the same quantity of heat that it contains first. It's basically a way of saying that that heat is conserved. And then he writes, this fact has never been questioned. Many experimental facts appear to support it, but it is almost inexplicable in the present state of the theory. So he can't believe it, but he thinks, if I deny this, then people will not read my book. And that's more or less why I think that he is even a greater scientist that people have acknowledged. And my guess is that if he had basically been brave enough to disregard the people had said, he probably would have created the entire formalism of thermodynamics already. Anyway, but that is Carnot. And so thermodynamics only emerged later when people started to see that heat and work were two versions of energy. And I'll just focus on the second law of thermodynamics. Then we know there are three laws. And rather than going through the mathematics, I'll just show the mathematics as a cartoon later on. I'll just quote from a song that was made by two British comedians in the early 60s. And they had a song about the second law of thermodynamics. And the song goes, heat won't pass from a cooler to a hotter. You can try if you like, but you're far better notter. And so basically what it says is that the second law of thermodynamics is a very simple observation, namely that if you bring two bodies in contact, that heat will flow from the hotter body to the colder body. Now, it's a bit of a circular reasoning, because how do you define what's hotter and what's colder? Basically by saying which direction does heat flow. So actually you have to be a bit more careful and say, if I have several bodies, like the heat flows from A to B and it then flows from B to C, then it will also flow from A to C. So that's the way you can order things according to temperature. And once you have a temperature ordering, heat will always flow from the hotter body to cooler body. That is the second law of thermodynamics in its I would say direct observational version, but that was not enough to create thermodynamics. And so the creation of thermodynamics was something that happened later, and was, I would say, in my view, largely the work of Clausius, Rudolf Clausius in Germany. You see, he's a very serious-looking man, and he wrote several articles where he built up much of the framework for thermodynamics, and in doing so, he came to the conclusion that there was a quantity that he called entropy. And so, as I said, I don't go through the derivation, but basically the argument of it is very simple, but that's not the center of my talk. But what Clausius said is that you can then show that if you have a system that undergoes a spontaneous change, a closed system that undergoes a spontaneous change, then the entropy, whatever this may be, this thing necessarily cannot decrease, and usually it will increase. And so that's the final statement in the sense of what Clausius said about entropy. Here it's the German version, but okay, Gerhard will recognize it. And so that was really the starting point of thermodynamics as a discipline that allows you to relate material quantum properties. Now, the only thing that Clausius did not tell us is what is entropy. So he actually is he certainly has ideas about what entropy is, but he didn't want to mix his derivation of the second law of thermodynamics with his personal interpretation of entropy. So that was, in a sense, you could say, to protect his claim on the second law. So it took a while before people started to have more than a verbal theory of what entropy was. And of course, the key person in that whole development is Ludwig Boltzmann. Here is his grave. I mean, I took the picture when I was in Vienna, or one of the first times I was in Vienna, where you have this famous formula. The famous formula. Sorry?
Just as a comment, if you look on the bottom right, you can see Paula Boltzmann. She's my grandmother, you know.
Ah, right. Yes,
She's the mother of my mother. And my mother unfortunately died, and she is also now in the same grave.
Yes. So I think that I took this maybe about 15 years ago, this picture, something like that. And anyway, so the equation that is on Postman Grave relates the entropy, here on the grave at least the symbol S is used, but let's not talk about which symbols people use. And the key statement that is made here in this famous equation is that the entropy is related to the log of the number of states in which a system can be. And the number of states of a system at the time of Boltzmann was actually a bit arbitrary. And the ability that you could count the number of states of a system at a constant energy and volume only became meaningful when people had quantum mechanics. So in this form, the equation was only written down by Planck, but Max Planck and also Albert Einstein were great admirers of Boltzmann. And so when the monument was placed, and Gerard will know much more about the details, they thought that this would be a very fitting thing to put on the stone. So that's the S is K log W. So the entropy of the system is related to the log of all of the number of states that the system can be. So in quantum mechanics, the states, you have discrete states, and for a given energy, you may have huge numbers. I mean, there are super astronomically large number of states. And then if you take a log, you get something that actually behaves like the physically observable entropy. So that's in words what it is. And in classical mechanics, the way Boltzmann approached it himself, this W has to do with the accessible volume in phase space, and that a phase space is basically a high-dimensional space that is spanned by all the particle positions and all the particle momenta. But I will not go into the technical bit because actually just considering it as a way of counting the number of states of a system is easier to explain and to work with. Now, for people in the physical sciences, this may be totally adequate, but of course, for if you try to explain the meaning of the second law to an audience outside science, they will not immediately say, "Oh yeah, of course." And so what has happened with the second law is that the interpretation has shifted over the years. And so if you look, for instance, at Wikipedia, it says that entropy is commonly understood as a measure of disorder. And this is a very popular way of thinking of entropy. And I would say, and usually it is even true. I mean, it is oh, sorry, I have to do something about my laser pointer. Oh, wait, sorry. Because I don't know where is this. I cannot do it. I temporarily click it away because I want to click this away. Okay. Do you see the arrow too or not?
Yes, I see the arrow. Yes.
Oh, okay. So basically, this is the way people normally think. They say, "Oh, entropy increases means or disorder increases," and that's more or less what you see on your desks. That if you don't clean your desk regularly, that it becomes more and more disorder spontaneously. And as I said, it's usually the correct way of thinking about entropy, but it is not the second law. And to show that there's a distinction between order and disorder as we see it, and entropy, I'll take a few things discuss a few things that were well, in a sense, developed much later in the middle of the 20th century, and where my own field, namely computer simulation, played an important role. And so to take a prototypical example of a transition from a disordered state to an ordered state, let us consider freezing. And when I was a student, an undergraduate student, people said, yes, it is okay if a system freezes, then clearly this is more ordered than that. So the solid is more ordered than the liquid. And so you think that the entropy here is lower. But then they say when it freezes, as the atoms and molecules attract, they can release heat, and the heat increases the entropy somewhere else in the system, so that the net result is still an increase in entropy. That was more or less the way people thought about it. until, I mean, about 1940, when there were two people, Elizabeth Monroe and John Kirkwood, who said that actually you can have crystallization in systems of particles that repel each other, that can't overlap, but that don't attract. And I mean, and John Kirkwood is very well known, but he did many other things in statistical mechanics. Elizabeth Monroe actually is very interesting person because she did this and many other things. I just want to say a few words about Elizabeth Monroe, just to say what kind of person she was. I mean, she was a student in the U.S. at Bryn Mawr College, which is a women's college, and when she studied, she was supervised by Emmy Noether, the mathematician who had escaped from Germany and came to Bryn Mawr, where she became professor. She actually died shortly afterwards, but she found that this Elizabeth Monroe was very smart, and she would like her to do a PhD, but that was not possible at Harvard, and so she sent her to Cambridge actually, and so she worked with my predecessor, John Lennard-Jones. And Lennard-Jones at that time was head of the emergent computing lab in Cambridge, where they did computing, but using a mechanical computer. That is the Cambridge differential analyzer, which is made of Meccano. This is a children's toy to make things. And actually, when I was head of the department in my office, I had the manual for this machine. So it was still there. It is still there. So basically what Elizabeth Monroe did was she worked on very early quantum chemical calculations, and then she went back to the US, and she worked indeed with John Kirkwood, the person I just mentioned, where she worked on the freezing without attraction. And then just after that, her life took a turn because she married, she got a child. And although this looked like a happy photograph, actually it's a bit of a sad photograph because the child got encephalitis, and this was around 1945, and it was treated with the early penicillin, which was a rather aggressive substance and suffered brain damage. And then Elizabeth Monroe discovered that there was very little support for people with brain damage, and so she started to work for the right of mentally disabled people. And when in 1962 the first Mental Disability Act was signed by President Kennedy, Elizabeth Monroe was in the room because she had been really driving this. So you see that sometimes a career in science can go in a very, very unexpected direction, but I still think that the scientific training prepares you for many activities in life. So that's Elizabeth Monroe, who said that you can have freezing without attraction, and that was very strange. And so they said, in principle, if you have hard particles, like small spherical particles that don't attract at all, but just can't overlap, they should be able to freeze. But the problem is, of course, how do you test that? Because no material known at that time behaved like that. And so that's where computer simulations came in. And I'll just very briefly say two words about the main tools in computer simulations. Namely the so-called Monte Carlo method, which is a method where it allows you to compute equilibrium properties of many body systems, and the molecular dynamics method, which is effectively just taking a system of many particles, and initially it was a few hundred, now people may take millions, and solve Newton's equation of motion to just see how the system evolves in time. And I'll say very little about the techniques. I mean, this is, of course, more or less how it started, in the sense that in the early 1950s, the computers that had been developed in the preceding few years at the US national laboratories, they first became available for other projects than just military projects. And so there was a group under the supervision of somebody called Nicholas Metropolis, who was exploring scientific applications. And John von Neumann also, of course, one of the key people behind the development of the electronic computer. And the Monte Carlo method really emerged in 1953 with a collaboration by 5 people: Metropolis, Rosenbluth, Teller, and Teller, who actually wanted to apply computer simulations to unsolved problems in physics. And one of the unsolved problems in physics at that time was indeed a theory of the liquid state, and in particular, whether or not you could see freezing without attraction. And so this is the article. I can say a lot more about what determines the list of authors, but maybe we can leave that for the discussion. I just want to show, if it works, a small recording that I made of, this is Marshall Rosenbluth. It was this one. At the 50th anniversary of the Monte Carlo method introduction, because he actually in this presentation says that actually what they wanted to do is molecular dynamics, that is, solve Newton's equation of motion, but it would have been too expensive, right? So could you hear that?
No, we could not hear.
Okay. Oh, okay, sorry. Okay, so basically he says the first thing that we tried was the obvious one, namely molecular dynamics. But at that time, that would have been too most expensive. And so then actually talking with Teller and Edward Teller, that is, and where is Teller on this? Oh yeah, so here Edward Teller, Teller and also probably with John von Neumann, they came up with this Monte Carlo scheme that is incredibly powerful, interesting. It's probably one of the most important algorithms in computing of the 20th century, and that has been. I mean, I used it extensively, and it's a marvelous method. But that's only one of the 2 methods to study systems of many particles. The only thing I wanted to say is that there's one person here, Ariana Rosenberg, who was very important in the development of the method, but who retired from physics. And so at this meeting in 2003, where they celebrated the 50th anniversary, one of the people who organized the meeting asked her about her reminiscences, and he says she really wasn't aware of the impact that it had. She said, "Oh, it's that thing." She was surprised that anybody even remembered it. Ariana Rosenbluth died just over a year ago, I think. The other method is molecular dynamics simulation, which I would say has been incredibly important. I think that there are by now probably millions of papers using molecular dynamics. But the idea behind molecular dynamics is not what I would call a discovery. It is just solving Newton's equation of motion, but not for 1 or 2 or 3 particles, but for hundreds, thousands, or millions. And these are the people who wrote the first papers on the subject: Bernie Older and Tom Wainwright. And again, you see that actually on the picture there are 3 people. There's also Marianne Mensai. And Marianne Mensai was actually quite important because she was the person who wrote most of the codes and ran most of the codes. And so I knew her because she was never an author, but she was always acknowledged at the end of the paper. And so at some point at Bernie Older's 90th birthday, there was a small dinner, and I saw that she was there. So I asked her about this and whether indeed she wrote the programs. It says I did write the programs, I did run the programs, and so I have here a picture of Bernie Older and Marianne Mensai 50 years later, and they say, so you see here, if you look carefully, that says Marianne Mensai. So you see that there's always more people involved in these discoveries than you would see from the literature. Anyway, the important thing is that Bernie Older with his molecular dynamics method, and also somebody called Bill Wood with Monte Carlo calculations, computed the relation between the pressure and the volume of a system of, in this case, hard spheres. And hard spheres don't attract. So if you think that for freezing you need attraction, this wouldn't freeze. And then actually what they found is if they decreased the volume, the pressure would go up and up and up, and suddenly it would jump down. and you would be in a different state, and that turned out to be a crystal. So you'd see a spontaneous transition from a liquid to a crystal at constant volume in a closed system. So the energy is constant. There was no exchange of energy, and that is precisely, this can only happen, this transition, if it means that the entropy of the solid is higher than the entropy of the liquid at the same density. So that was a striking confirmation of the predictions of Monroe and Kirkwood. And it created a huge debate at the time. But people, I mean, there was at some point a debate involving 16 roundtable discussions with 16 participants. There were 2 Nobel laureates and another number of extremely famous scientists, and they couldn't agree. And so George Uhlenbeck was the chair. And after a while, he said, well, I mean, I think we can't resolve it, so let's vote. And 8 were in favor and 8 were against. And George Uhlenbeck said, yeah, actually, I can't believe it either. So they voted it down. But of course, in science, you don't decide things by voting, you decide things by testing. And so that over the years, it became more and more obvious that it does happen. And importantly, much later than the simulations, there were experiments done on colloidal systems, and you can make colloidal systems that really behave like hard spheres without attraction. And this is experiments by Peter Pusey and Bill van Meegeren from the 1980s, where they looked at suspension of colloidal particles at different densities. And as you increase the density, here you see just the dense liquid, and then you see these small grains, these colored grains, they're crystals, and they're colored because what you see is the Bragg reflection of the crystal, because the lattice spacing in these crystals is of the order of visible light, whereas for atomic crystals, it would be the wavelength of X-rays. So they really could test the older Wainwright prediction and found that it agreed extremely well with their experimental observations. So that, I think that since then, most people have accepted that this entropic freezing is really happening. And at the moment, there are many, many, many other examples of transitions where you start from a disordered liquid, go to a highly ordered solid. So this is AB13, a very complex binary solid, where the transition, again, is not driven by attraction, but is just driven by the fact that this state has the higher entropy. Now, I should again add a bit of a disclaimer, because I focus now on the fact that entropy may act as an ordering principle, but very often ordering is due to energetics. And so I'll say now a bit more at a situation where ordering is due to energetics, and then at some point you'll see that entropy comes in through the back door. So that's my general introduction. Now I start talking about something that seems very different, and I would like to say, bear with me, because at some point there'll be a link to entropy. And so this is actually a topic that I've been working on for a while, but it has recently become, in a sense, more relevant, because if you look at I mean, viruses, for instance, but also bacteria, viruses bind to specific cells. They bind, namely, to receptors on the surface of cell, namely those that are overexpressed on some cell surfaces, and those are the cells that the virus targets. And once they are bound to the surface, then they go out endocytosis. That means they go into the cell, and then they can multiply if they're lucky. So that is the way viruses bind to cell surfaces. And the question is, how do they recognize which cells to bind to without spending too much time binding to the wrong cells? And so just for this SARS, the coronavirus, the receptor is called ACE2, but that's just the name of a receptor. Okay, so what happens? This is my very schematic drawing of a virus. I mean, at the beginning of my talk, I had an artist impression of the virus, but the viruses are, at least the coronavirus, is a sphere that has a large number of spikes, and these spikes are essentially proteins that, and the tip of the protein can bind selectively to this ACE2 receptor. But you see, there's not one, there are many of them. So it can bind 0, 1, 2, 3, etc. And these bonds go on or off. They're not particularly strong bonds as such. So this is in a situation where it would be all unbound. And so what you first have to look at is, so suppose that I keep the distance between the virus and the cell surface fixed. What is the probability that the two are bound? Well, this is something that in principle, I mean, it's almost impossible to measure, but it's something that certainly in careful computer simulations you can estimate quite well. And you find that there's a certain probability that this spike will be bound, and that 1 minus the probability that it will be unbound. I mean, it's that there's nothing special about that. But what I want to focus on is what's the effect if you have many spikes. So it's maybe a bit redundant, but it is convenient to express the ratio of the probability to be bound and the probability to be unbound in terms of what's called a free energy. Why do I do that? Because typically when people talk about attraction, they talk about the binding strength, so the energy of interaction. And here it's really a free energy of interaction. And you can just define it as the log of the ratio between probability of being bound and unbound. So this defines this free energy. And you can just interpret this as a binding strength. And the KT is the thermal energy. This again is Boltzmann constant, so we see B again. And so this is the for a single receptor. So this is the receptor. This is the ligand for a single pair. This is what determines the binding probability at a given distance. Now you can rewrite this, and I'll do it, and just say what's the probability that the receptor is unbound, and this is simple mathematics. And basically what it says is if this attraction is very strong, that means this is very strong and negative. This becomes a huge number, and it's almost certainly not unbound, it's bound. And if this is for instance, positive, so they don't really like to bind, then the probability of being unbound is very, very large. I mean, that's more or less what you would expect. Now, the thing is, what happens if you don't have one, but you have n? So you have n spikes and n receptors. And I assume for the moment, it is a one-to-one situation where you can have one spike, one ligand binding to one receptor. Then you get this situation, but the probability that all of them are unbound, and I just now assume that they bind completely independently, which is an oversimplification. But if I assume they're all unbound, that's the probability that a single pair is unbound to the power n. And that makes a huge difference, because if you have weak binding, which we typically have, and I will not go through this bit, then what happens is that the probability that you're unbound, you can write as an exponential form. And the main thing is that what you see is that the probability to be unbound depends now, it decreases exponentially with the number of ligands. So you can see that you're now suddenly very sensitive to the number of ligands, and of course to the binding free energy. Now that is important because, so there we have this again. It means that viruses that can bind strongly to a cell with large number of receptors bind very weakly to a cell with only fewer receptors. So this is the basic mechanism that helps viruses identify which cells to bind to. Now the thing is, you'd say, oh, that's bad news, because that the viruses use all these spikes to bind to a cell. It is bad news in a sense, but it's also good news, because as you see, if you can tweak this binding free energy, this binding strength a tiny bit, then you can easily go from something where everything binds to a situation where nothing binds. So I think it also indicates that there may be relatively innocuous ways to suppress the binding of viruses to cells, and whether that's true or not probably depends on many other factors than I as a physicist can see. But okay, that's the underlying idea. So the things that are important is what is important in the binding. It's the temperature, it's the binding free energy, the binding strength, and it's the number of ligand receptor pairs. Now, I said, but entropy will come back, and entropy does come back because my drawing was oversimplified, because I assumed that these receptors were all fixed in space, etc., and they're not. And so to show what happens if you can bind in many different ways, so you have different ligands and different receptors, I take an example from a slightly different field, namely that you have colloidal particles that have been coated with DNA. This is a subject that emerged in the late 90s and is at the moment incredibly popular because it allows you to design certain materials. And we did work on that, but I will not talk about that. The main thing I want to say is, suppose that I have two colloids that are coated with DNA that can hybridize with complementary DNA. And so I have here one colloid coated with one type of DNA. It's very long, and this is another type of DNA, and these two combine. So if I wait long enough, then what you see is that these things start binding, and you can, sorry. And as you see now in this particular case, all the bonds are satisfied. So you say this, if this is a strong bond, this would be quite inert. It couldn't react with anything else, or it can't bind to anything else. And so already quite a while ago, we did simulations of this system to see what would happen. And so we put this particle in the model system in a simulation. And at low densities, you see they form dimers, just as I expected. Actually, sometimes it looks like you form larger clusters, but that's because this is a projection of 3D simulation on a 2D plane. So you see all these dimers, and then you increase the density of the system, and you think, oh yeah, you get a higher concentration of dense dimers. But no, that's not at all what happens. What you see suddenly is that all the particles collapse into a dense clump. They form a dense percolating network. And so the question is, that's strange, because they had already all the bonds formed that they could possibly form. So it cannot be due to the binding free energy, because that's completely satisfied. So the reason why the system still undergoes a phase transition is because you can hugely increase the entropy of the network, of all the ways in which you bind things together by allowing particles to bind to different partners. And so, to give a very simple example, I'll take this out. Sorry, take this very simple example. Suppose that I have here flexible ligands that can bind to the receptors, and here there are 3 receptors, and you can see that if they're flexible, there are 3 factorial ways you can connect these ligands to the receptors. But if you have more receptors, then the number of ways you can do it is just the Newton binomial distribution. It becomes much larger, and as soon as you have larger, I mean, not just 3 or 6, but you have larger numbers of ligands and receptors, these numbers become quite large. Now, why is that important? Because if you take the log, you have the entropy that's associated with it. And this entropy favors binding. So you get a huge entropic enhancement of binding to surfaces that have a high concentration of receptors. And that really helps the viruses identify which surfaces to bind to. So to just summarize that point, if you have a target cell with a high number of receptors, you would like, or the virus would like to bind to that. Whereas if you have a cell with a small number, you would not like to bind. And I say here that it's a virus, maybe a microbe. But of course, this could also just as well apply to drug discovery, to drug development. If you have a particle that delivers a drug, you want it to bind to the cell that overexpresses the receptors that are associated with the particular disease. So many cancers have a situation where certain receptors are overexpressed, and you would like to bind to these and not to these, because that would just give you side effects. So many of as we all know, many of the effects of anti-cancer drugs is that they give terrible side effects. And if you can selectively just only bind to the target cell, that would make a huge difference. Now, this is just an example of what actually happens in the simulation, just to illustrate the point. Here, the red dots are supposed to be ligands. So we took a surface with ligands, and here we take the same surface, but with a higher concentration of ligands. And here we have, well, I mean, it could be a particle, but let's call it a virus. And this virus has only one ligand. So these are the receptors. Yeah, they have only one ligand. And so if I increase the concentration of receptors by a factor of 3, then the number of particles that bind goes up, but not even by a factor 3. I mean, it's maybe a factor 2 only. If you take exactly the same system, but now you have not one ligand, but you have 10, and you increase the concentration of the surface the receptors by a factor 3, you see that suddenly the number of bound particles goes up by an order of magnitude. Effectively, what this shows is that you become extremely sensitive to the surface concentration of receptors. And that behavior is called superselectivity. So you're highly sensitive to the concentration of the receptors that you're interested in. And that, I think, is incredibly important. And so if you can, I mean, if you can use the trick that the viruses use to distinguish between these expression levels, then basically humans could do that too. And I think the pharmaceutical industry could and should do that too. And at the moment, on the whole, they don't. So the thing that they do typically, I mean, if you think about many drug delivery mechanisms, they use monoclonal antibodies. And monoclonal antibodies are basically things that recognize a certain receptor and bind extremely strongly. So yes, they target the cells that they should target, but they also target all the cells, and there are usually many more of those, that have the same receptors at the lower concentration. So I think that here there's a lot to be gained. And I just want to very briefly say that you can use this same idea of multivalent in doing some genomic testing. It's an alternative to what people use normally when they do PCR testing of well, the PCR test, say, of the COVID. You can also use this method to use something quite different, but I will not go into much detail about it. I just want to show the effect of the multivalency on the binding probability. So here I made a schematic picture where I considered, in this case, 4 different particles that have different numbers of ligands. And I made the choice such that they all have the same total strength of binding. So at a particular receptor density, when they bind, they're all the same. The only question is, how quickly do they respond to the change in the receptor density, so the number of receptors on the cell surface. And the black curve is when you just bind with a single receptor and a single ligand. So that's what the normal thing would be. And what the important thing is that in order to go from 10% bound to 90% bound, you have to increase the receptor density by 2 orders of magnitude. If you have instead 10 ligands, so you have like the spikes of the virus, and you want to go from 10% to 90%, you see it's only like a factor 3. So you suddenly become much more sensitive to the receptor concentration. I think that's a thing that really is important. Now, this was what we did theoretically, numerically, and since then people have done a number of experiments. I'll just show you here one. This is an experiment by Galina Dupacheva and Ralph Richter, who looked at a self-assembled monolayer of I think it is it was in this case ferrocene on the monolayer, and this is on the other side. It is hyaluronic acid. This is a long chain functionalized with cyclodextrin, which is basically a cap that can bind to these monolayer particle, to the ferrocene on the monolayer, and you can change the concentration here. And so that's what basically happened here in these experiments. They looked at the change in the concentration, and then looked at how much was absorbed. And rather than going through the picture, I'll just say what it says, basically, that indeed in this experiment they found that the behavior was compatible with this super selective behavior, that it was actually that the number of particles bound increased much more rapidly with the concentration of the ferrocene on the surface than you would expect if it would be just a single particle binding, a single receptor binding to a single ligand. So that was extremely encouraging. And since then, there have been more experiments. And I'll just, if you don't mind, skip the bit about the gene detection. I'll just say that it is a way we can actually also in principle detect specific genomes. So this is an idea that was developed by Rosalind Allen then in Edinburgh to see if there could be simple tests to distinguish between bacterial genomes and viral genomes. And the reason is that if you want to give people, if people have a bacterial infection, you want to give antibiotics. If they have a viral infection, you don't want to give that. And so it is important if you can quickly distinguish. And this was a method that she proposed that should allow us to distinguish quickly. But as I said, I will not go into that, although we are pretty hopeful that this might be something useful. Okay, I come very close to the end of my present.
May I
Sorry.
ask one thing?
Yes, please.
Yes. So this phenomenon by multivariant and this binding is what you may call entropy condensation.
Yeah. Yes, exactly.
Then, at the introduction, you talked about just phase transition of the hard sphere without interaction.
Yes.
Then, from the liquid phase transition from liquid to solid means the entropy increases.
Yes.
Okay. So this is counterintuitive phenomenon.
Very, very counterintuitive indeed. Okay, yes.
Okay. Thank you.
Okay, thank you. So basically, here I summarized the points about the distinction between the monovalent binding, where you bind with a single receptor, basically explained that this is not a virus that exists, because this virus, if it would exist, would bind to a single receptor, and that is not effective because it cannot distinguish very well between cells with many receptors and with few receptors. And so this kind of virus doesn't exist. The ones that actually do exist are the ones that have many spikes. Basically, it tries to explore how many receptors there are within its own size, more or less, on the surface of a cell. And those viruses are the ones that we have to deal with these days. So those are the thriving viruses. And I said, and I hope that this is also a way to improve drug delivery. Now, I'm come to the end, so I'll just say one thing that for those of you who also have a Trinity link may be amusing. And that is, of course, in 2020, when the corona pandemic was already basically underway, it was clear that it was spreading. I mean, I think that since late January, we knew that people who had no symptoms could spread the disease, and they could take airplanes, they could go anywhere. So there was a pandemic. And so it was in at some point in early March 2020, I was just wondering what the university was doing to prepare for the pandemic, because I was convinced that there would be a lockdown. This was early March, so I think that I looked at as you know, in Cambridge you have the Cambridge University reporter that it sort of informs the community of all measures that the university is taking, all the bylaws, all the decisions, but also if there would be a COVID policy in place, then it would have appeared there. And so I used the university site and I looked for COVID, and I'm not sure if I can see the date, but I'm pretty sure it was March 8th.
March 11, it says at the top, if you look.
Oh, March 11, where?
11 March. If you look in the red box up on the top.
Oh, yes. Oh, so that's blocked at the moment for some reason.
Okay. There's a red box
for me,
where it says March
11.
Okay,
so it's March. Oh, it's March 11. Okay, great. So it was 12 days before lockdown in the UK. But I mean, it was clear what's happening already. So we looked for COVID, and then Cambridge, being a very classical university, said, no results found. Did you mean Ovid? And of course, for those who study the classical languages, this would be a very obvious answer. But at that stage in the game with the whole pandemic, I was a bit surprised. But by now, if you look for COVID, of course, you find a lot more. But I was a bit late. Anyway, I think that I would at this stage like to switch over to see if we can have some discussion on the topic. I thank you very much for your attention, and so I'll stop talking here now, and we can then discuss entropy and multivalency or other things. Thank you very much.
Thank you so very, very much for this fantastic overview, and also very topical on COVID. So maybe I'll directly on the point you made at the end, the preparation of University of Cambridge to COVID.
Yeah.
We just had on Tuesday this week, we had a dinner here in Tokyo with a master.
Yes.
Sally Davis, who before, of course, is a health expert, and she was the chief of, I forgot exactly the name.
Public Health England.
She was the chief of health systems for...
it's a PHE, Public Health England.
And she was giving us a short presentation at the dinner.
Yeah.
And one of the topics she covers was also how she prepared Trinity for COVID.
She did very well. Yeah.
She was saying that she, I don't know about the Cambridge University, but what she was saying is that Trinity, because of her knowledge, she was sending people home immediately at an early point in time, which at that time was attacked. And she said many people disagreed with her. But later on, they were grateful because they were avoiding the big rush where all the trains were full when people were returning home.
Absolutely.
So she was apparently taking very informed decisions because of her professional knowledge. And so Trinity, I think, was well prepared because they had the right person.
Absolutely. I should also say, maybe it's a bit off topic, but in this context, of course, what happened in the beginning of the pandemic is there was a lot of confusion, but there was at that time in the UK, the government policy, which was based on the modeling of the group at Imperial College, was aiming for herd immunity. And I was discussing with my colleague, Michael Cates, who is also at Trinity, and he's the Lucasian professor, so he's officially the successor to Newton. And we said, well, there are many possible models, and it would be extremely dangerous if one model at this stage comes to dominate the whole story. So, but then it was a bit difficult to get overview of the literature because there were thousands and thousands of preprints all the time. And this is something that actually we discussed with Dame Sally, whether it would not be a good idea to have volunteers, really bottom-up volunteers, scan the preprint literature and then try to select articles that were not just scientifically interesting, but that have possible policy relevance, and then make sure those articles went to SAGE, that's the advisory committee for the government. And we checked with the people at SAGE. So Mike Gates had contact with Julia Gog, who was on SAGE, and he said, would this be useful if other people would do this? And she said, yes, it would be useful, because they were so busy running models all the time that they really didn't have time to keep track of this huge literature stream. And so we set this up actually with the Royal Society. So they basically hosted a website, and we got volunteers. We got, I think 400 people registered, 200 people did something, but actually 40 people did quite a lot, and maybe 10 did an enormous amount of work. And so I think we in total scanned something like 750 preprints. And of those, a small number, we said, this is could be policy relevant. And then the Royal Society had agreed that they would then make sure that those articles that we considered potentially interesting, they would be refereed within 24 hours. And if the referee said, yes, this may be interesting, then it went to SAGE. And what happened after that, we didn't mix, because I believe very strongly that you should separate the science from policy advice. I mean, the science should be, in a sense, not involved in the decisions. That is something for SAGE and even more for the government. They make the decisions. But I think that was an incredibly useful exercise to basically leverage the power of the scientific community to scan articles. And the interesting thing is that initially the people doing the reading were mainly modelers who were looking at the models, but then increasingly we also got people who understood more of the biology, biophysics, etc. And so I think that if I look at the people who made most contributions, one was a PhD student, one was an archaeologist from Oxford, and one was a radio astronomer from Edinburgh. So it's a very interesting club of people, but yeah.
There's a
okay. Sorry.
No, this is fascinating. I mean, there's a little bit off track now, but I had a conversation in 2018 when I was many times in Cambridge, and I had two separate conversations with Sir Greg Winter, who of course is a molecular biologist, and also with Lord Martin Rees, who is an astronomer. And I heard from both. I discussed that with both, and what I condensed from these discussions is that Sir Martin Rees, he's very concerned with disasters which destroy the Earth or our human life on Earth, and when he talks about this, he says the things he is most afraid of are biological issues. He thinks that life can be most threatened by something like out of control viruses, But on the other hand, Sir Greg Winter thinks that biology is all under control. He was saying that he thinks that evolution is so effective that all experiments had been already done on the humans. Like human is already evolved to a point where humankind is resistance to any biological attacks, he was saying. So therefore, he is most afraid of, objects from space hitting Earth, like other, So the interesting point of that was that each one of these, outstanding experts in their field were they felt that their own, the fields where they are active are under control, whereas the uncontrollable dangers to life on Earth comes from the other side. Do you know what
I understand what you say. I must say that on the whole, I tend to agree with Martin Rees on this. I think that humans have evolved to deal with most known viruses, but as soon as you have a truly new virus, nothing protects you. I mean, if you look at that, because human evolution is not something of the past few hundred years, and so if you look at the Black Death, so 1347-48, or you look at the Justinian plague in the 6th century AD, those killed maybe 30, possibly 50% of the population, in spite of all the evolution. So I mean, the question is, would a virus wipe out the human race? No, probably not. But it would be, again, the survival of the fittest. And if only like 20 or 30% are fit enough to survive, it would still be a major disaster and a total collapse of all societies.
Maybe Professor Fukumoto, we could discuss a bit more about this counterintuitiveness of the entropy-driven phase transitions. I think that I was also, when I was preparing for the discussion with you, I hadn't heard about this before, So that is a very interesting issue. So maybe we can, if you like to discuss a bit more about that, Fukumoto-sensei, what do you think?
Thank you. First of all, I was impressed by the name Leonard Jones.
Yes.
Professor Jones, yes. Because this is a legendary name, and the potential of Leonard Jones
Yes.
12 R12 and
Yeah, 12.6.
6 is very
Yeah.
popular, and now I'm very intimacy to you, and then so.
But sorry, can I say just one thing about Leonard Jones? So the thing is, he actually, as far as I remember, he was working on different potentials, basically because in the early 20th century, people were able to solve the Boltzmann transport equation for simple power law potentials. And so using the method of Chapman and Cowling that was developed around 1910. And by the way, which is not a particularly nice procedure, Chapman wrote, it was Chapman and Engelsgaard, but Chapman and Cowling wrote a book about it. And Chapman, when he retired in 1957, he gave an interview and he said about his own book, it's not easy going, it reads like chewing glass. And indeed, it is a dense in equations. But Leonard Jones, when he actually did his work, he was I think he was still at Trinity. He was still called Jones, not yet Leonard Jones. And so he was I think a research fellow at Trinity for a while, and then he went to Bristol, and there he married a lady called Leonard, and then he changed his name, and then he came back to Cambridge. But then he was not at Trinity anymore.
Interesting. Yeah. Yes. And then let's come back to the entropies.
Yeah.
This filtration of hard sphere is just a surprise to me. And then at the time you mentioned about entropy. One feature of entropy is a disorder, or this extent of disordering, and also this phase transition is not this category. And you emphasize second law of thermodynamics, and this disorder and order feature is not the same. So
no.
Yes,
can yeah.
Can you explain this?
Yeah, I will try to explain it. The thing is that the key point is that what we see as order is not necessarily the microscopic sense of order. In the sense you would think order has very few realizations and disorder has many realizations.
Yes.
But actually, if you look at it microscopically, that is not necessarily true. And let's take again the spheres as an example. Suppose that you have spheres and you throw them in a container, and this is something that people have been doing, like in particular J.D. Bernal, but many people have been doing. If you throw them randomly in a container, then they don't form a crystal; they form a glassy structure, and you can fill at most almost 64% of the space, so 2/3 of the space, and then they jam, and then they jam. The spheres can't move at all.
Right.
Now you take the same spheres, you carefully pack them in a lattice, a face-centered cubic lattice or something like that, and then you say, okay, and I put it in a volume, and I make sure that the total volume is such that the fraction of the volume occupied is the same where the spheres would jam if you just throw them in, so 64%. But then they still have space. You can shake them and it will rattle. And the reason that for a crystal to actually have it jam, you have to go to the Kepler packing, which is 74%. So there is a range of densities where the particles still have freedom of motion in the crystal, but not in the disordered state. So it is basically, if you say, I associate entropy with freedom of motion, then there's no problem at all, because then, yes, the second law says you'll always go from a state with a lower freedom of motion to one with a higher freedom of motion. And usually that corresponds to with visual order and disorder, but in some cases it doesn't correspond to what we see, but really it's a bit more microscopic. Does that help a bit?
Yes, just there is a problem of English listening. Yes.
Oh, sorry. Maybe I speak too fast.
Right. Yeah. Just a regular lattice of crystal is not so-called closest packing, right? And more particle can be accommodated.
Yes.
Yes, and then in this glassy state, this jamming state is most packing, right? And so order and disorder means order and disorder is not the same as freedom of packing. So
yes,
even if ordered, we can have more freedom to pack.
Yes,
And so
exactly.
this will increase entropy.
Yeah. Yes.
Right. Now, yes. Now I.
Okay. Thank you so much.
Yeah,
That's
yes.
very good. Yeah.
Yeah.
Yes.
Good. Interesting.
Yeah. Thank you. Garrett is looking at the screen.
And
I don't hear you. You're on mute, Garrett.
Yes.
You're on mute.
I was just typing because one of them, our members, Mickey Donaghy, who was a computer scientist, he was busy with other things and he was thinking to join. So I sent him a message that in principle he could join now, but it's a bit late now.
That is probably true, yes.
I think he will have to watch it on the recording on YouTube afterwards.
Okay.
Yeah, it's fascinating for me that your book also starts with entropy, and your talk today starts with entropy. So entropy is so central to everything and also to your work. That's really, really fascinating. And when Cedric Villani gave his talks here in Tokyo, there are different faces to entropy. And one is the entropy in information science.
Absolutely,
and
yes.
Maybe you can talk a bit about, there's this issue of looking at entropy as like you mentioned, many people associate entropy as something which brings about disorder or drives disorder or something like that. No? But another way of looking at entropy is look at it as the measure of information you can bring through through telecommunications channels, for example.
Right, absolutely, yeah.
And so maybe you can talk a bit about the phases of entropy. As you, through your computer simulations, you get a very deep insight, of course, because you calculate and you can look at make microscopic experiments on entropy, which you can't do without a computer simulation.
It is true, but I think that the information entropy and the physical entropy, they are distinct but not very distinct. And so let me clarify this as follows: that the thing about if you look at the second law of thermodynamics from the Boltzmann perspective, that it basically says that a system will spontaneously evolve from a situation where it has a smaller number of accessible states to a larger number of accessible states. It means that you need a protocol. I mean, Newton's equation of motions or whatever, you need something to go from one state to the other, a well-described procedure. If you look at the information entropy, there is no protocol that says that you go from a channel with a high information density to a low information, which would be the same thing as spontaneous. There is no protocol. I mean, it's a way of quantifying the information. On the other hand, if you look at the description of entropy, I mean, there's a famous paradox from the 19th century called Gibbs paradox, where Gibbs noted that if you have two gases in different containers and you remove the surface dividing the two, that the entropy of the two systems goes up because of the mixing. But on the other hand, if you take two gases that are of particles that are identical, then this does not happen. And I mean, in the 19th century language, this was quite mysterious. And the explanation that most people sort of adhere to certainly in until quite recently, is that it has to do with the indistinguishability, the quantum indistinguishability of particles. But that is an oversimplification, because if you take systems like colloidal particles, which are micron-sized particles containing billions of atoms, they are always different, slightly different. They may look perfectly identical, but they're different. And still, if you mix two sort of macroscopically identical colloidal suspensions, then the entropy as such is not changing. So what does that mean? That the entropy really, in this case, expresses our knowledge about the system. It does express the information about the system. The only thing is, what in a physics term does it mean that you have information? It means that there is at least conceivable an experiment where you can separate the two. If you can separate two components, then they're distinguishable. And you can talk about the entropy change. Why? Because if you can separate the two, you can think of building a Carnot engine, some kind of cycle, where you separate the two, do work, and then at a different condition, let them mix again and get work back. And so basically you have something where you put in heat and get out work. And that can only be done for things that you can, at least in principle, separate. Once you talk about things that you cannot even in principle separate, then it is pointless to consider them distinct species. I think that's, so there is a link between information and entropy, but it is different because as such, information entropy has not an arrow of time built in it.
Okay, so thank you so very much. I think we have discussed many aspects now.
Yep.
So, any more questions? No? So then we'll conclude, and hope to see you in Tokyo sometime, or in Cambridge.
Absolutely.
Next time.
Whatever.
Okay.
Okay, well, thank you very much.
Bye. Thank
you
you so
Bye.
very much.
Bye.
Thank you very much. Best wishes. Have a great day.
Same.